Okay, folks, we've talked about some basics of nucleic acid, some structural details, and now I want to get into understanding about the stability of nucleic acid. There are many types of non-covalent interactions that contribute to the stability of nucleic acid, and I'm going to talk about them in ascending order. So we'll start with the interaction that contributes but kind of contributes the least, and we'll end with the interaction that contributes the most. So the first type of interaction that you already know about is hydrogen bonding. Now, of course, hydrogen bonding is occurring between the bases, right? But let's remember what we already know about hydrogen bonding. Hydrogen bonding in aqueous solution is not going to be the strongest type of interaction, because if we break a hydrogen bond in aqueous solution, we can easily reform that bond with water. So hydrogen bonding and base pairing is important, in particular because the base pairing allows great alignment of those 2 or 3 hydrogen bonds, but it is lower on the rung of importance for DNA stability. Next up, in terms of importance for DNA stability, is pi-pi stacking. Pi-pi stacking occurs when conjugated systems kind of sit on top of each other. On the right-hand side of the slide, I'm kind of showing you a top-down view of one base stacking with a base below it. And what's happening here is that these conjugated ring systems of the bases form these kind of donut-shaped electrical clouds that perform favorable interactions with the donut-shaped electrical cloud of the ring below it. Now, this type of interaction is more of a London dispersion, non-polar type of interaction, because we think of these conjugated ring systems as kind of sharing their electrons fairly equally, so we don't have a very dramatic polarity in the conjugated ring system itself. Now, because this is a more nonpolar type of interaction, we can compare this to the hydrophobic effect. We have this nonpolar pi-pi stacking interaction happening. I am not good at drawing, so please forgive me. Happening on the inside of that DNA, hidden away from the water, minimizing contacts with water, and therefore increasing the entropy of water. So that is the second type of interaction happening in DNA, and it's occurring kind of down through the middle of those bases that stack on top of each other inside of that DNA helix. Finally, the most important type of non-covalent interaction is ionic interaction. Let's for a moment think about what's happening with the phosphodiester backbone of this DNA. Each nucleotide comes with its own phosphate, right? And each of those phosphates bears a negative charge. So as we build up this DNA, we have a lot of negative charge, because each of those phosphates adds a -1. So you can think of this massive polymer with a massive amount of negative charge. Coulomb's law tells us that having all of this negative charge so close in proximity to itself should be super unstable and repulsive. But we know that DNA is quite stable. So what's going on here? Well, I mentioned it previously in these videos, but you will always have the association of a divalent cation, usually magnesium, with DNA, RNA, or nucleotides. We need the stabilizing interaction between the positive charge of the magnesium and the massive negative charge of the DNA. This helps kind of balance out. This helps kind of neutralize that charge. And so that is the final type of interaction. That wraps up our material for today, folks. We started with some vocabulary. Do we know what a nitrogenous base is? Nucleoside, nucleotide. And then, for the real focus of today's videos, talking about the structure of DNA and different things that contribute to the structure, as well as stability. What non-covalent interactions lead to stabilizing that DNA? And with that, I will leave you with today's cat meme.